So out of the box, the relational database and the relational model was mainly focused on a single server. It works perfectly if your database can fit and can be managed on a single server. And your number of users can be handled on single server, no problem. As soon as this, the database volume or the data volume and or the number of concurrent access grows, then the scalability, there's a question mark there. And here, what I'm saying here, I'm saying really large database and a really large number of users. A normal application, I'm saying something like, let's say QNB or something like Amazon, one server, definitely not enough. You need much more. Sorry?
Facebook.
Facebook, oh, of course, those big guys are in the extreme. Those are kind of special cases. And not all companies will reach that global level with millions of users and millions of thousands of concurrent users, if not millions. We'll never know. So what I mean here is just for an enterprise, normal enterprise, you can still hit the big data problem. Okay, so this new movement started NoSQL, I think, around 2010. That's where it started to pick up. And I gave you some taxonomy of. So they came up with different data models, and they have partitioning and replication built in from day one. And they came up different data models. These are the main data models. So relational is not the only one. You don't need to have just the model that most of us are familiar with. You have tables, and these tables have relationships, and you use SQL to populate them and to query them. That's not the only way of managing data. Some databases, they are key value pair database. You only have, the whole database only have two operations, get and set, using the key. That's the only thing. Now, the value could be anything. It's up to you what the value will be. Now, of course, there is always a schema there. There is a data model, but your application needs to worry about it, not the database. Okay, and because it is key value pair, it's very easy to scale and to scale out, to have multiple machines hosting your database. There's another family. By the way, we'll have a lecture later on where I will demonstrate each of those through some examples and example databases. But now I just want you to have a high-level view of them. Column family database. Column family database, I try to show you small examples of how they look like. So you have kind of a key. So each, you can think of it as a row. It's not really a row like traditional row we have. You can think of it as a key, and the value is a name value pair. Name value pair. And you can see here in this small example here, this is the key of my row, and this is the value I have associated with this key. So these values has name of the column and the value, name of the column and a value. And you can see here, this is the same kind of, think of it, same table, but the schema is not fixed. You can have different schema for different row, okay? And each row is quite independent. Compare this to a relational database where the schema is fixed. So all the rows on the table has the same schema. And if some column is not relevant or is not applicable, you put null in that particular column. Okay. So here is another example. For example, the key is the name of the person, and this key is associated with multiple columns. And these columns, we don't need to have same columns for the same key. You can have different columns. The ones that are not applicable will not even appear there. Okay. For now, you can think of it as still a key value pair, but the value is a set of columns, name and value, name and value. And those columns are not necessarily unified across the whole table. You can have different columns for different rows. Yeah? And the other thing you can do here, you can query by row, or you can query by row and column. That's what this type of database give you. These are special cases, not very commonly used. The one that is really successful and really competing head-on with the relational database is the document-oriented. Yeah, the document-oriented is the most successful one so far because it is more versatile and can be applied in many scenarios. And here, the best way to understand this one, I gave you the example of an invoice. So an invoice is an aggregate object. So in an invoice, you have multiple things in one entity. So what I have here in a typical invoice, I have some details about the order itself. So it might be the order ID, the order dates, who the customer is. And then within an order, I have multiple items, multiple order items. And these order items could be related to some products and quantities. So here is the order item. Here is the quantity and the price and the subtotal for this line. So this can be stored in an order item. And then we have payments. It could be one or multiple payments for that particular order. Okay. So in a relational database, for sure, we cannot store it as it is. We have to denormalize it or break it down into multiple entities. And each, so if I want to create an order, I will be inserting into multiple tables. So to create this order, I have to insert the order in orders table. Then in here, I don't need to insert anything in customer, except if it's a new customer, I will need to insert it there. Then for each, so I have one insert. Let's suppose the customer already exists. So I have one order, one insert in the order. If I have 10 items to order, I have 10 inserts into the order items. And if there is one payment, one or many, let's say just one, I will have one insert here. So 1, 10 plus 1, 12 inserts to manage this, to create this order.
Altogether.
Yeah, altogether. And then when I want to retrieve it to display or to produce an invoice, I have to join again all these tables and bring this information back. While in a document-oriented database, you just keep it as one unit and you store it as one unit, you retrieve it as one unit. Okay, that's basically the idea. So most of these databases, in general, in the NoSQL database, they favor aggregate-oriented data model. So you keep data that are related, you keep them together. Okay. One thing you need to really keep in mind when it comes to data model, associated with data model, there is the query capabilities or the query language. And the data model heavily influence the query language or the query capabilities of your database. For example, for the key value store, if you have a key value store, what queries you can do on your database? Get instance. You cannot do anything else. The value is a black box. You cannot search based on the value. Now, for the document-oriented database, you can query the actual documents. So the value, it's still kind of key value, but the value is queryable. You can query. You can go here, for example, and say, give me the orders where the orders have more than 10 items. It can give you the orders, all the orders with more than 10 items. So you can, the document is not a black box.
We define its structure when we create it, the document.
Here, they call it kind of schema-less. You don't need to have a schema. Database does not care. But the application there is a schema. The developers will be aware that there is a schema, but database doesn't really care. There is no enforcement of a schema. And you can have typically like the way it works in this type of document-oriented database. You have a collection of databases. Sorry, you have collection of documents. Let's say customer collection, orders collection. Let's say contacts collection. And in these documents, you put documents that are related, but not necessarily they need to have exactly the same structure. They might have slightly different structure. It's up to you. But really, there is a schema, but it is the application is aware of the schema, not the database. Database does not care. But in relation, it's very different. Database is aware of the schema. In fact, you define the schema first. I mean, you let the database know your data model, which is also known as a schema. And then that's the first thing. You create the schema in the database, and then you start inserting, updating, querying. And while you are, let's say, inserting or updating, if you violate something in the schema, then the database will not let you do that particular action. For example, let's give an example. Let's say you have a customer table, and in the schema you say the first name and last name cannot be null. They are mandatory. You must supply them. If somebody tries to insert a customer and they don't provide one of those mandatory columns, database will not allow you to do that. But in here, there is no such thing. In the document-oriented, there is no schema. No schema for the database, not for the developer. Because as developer, you might need, for example, to know how many items per order. So you are aware as developer, you are aware that you are storing, let's say, orders in the orders collection. And you are aware that in the order, there is an order header, there are order items, there is a payment. Yes, you are aware of the schema, but not the database. Yes? Yes, please. Yes.
So, object-oriented database, are they part of the same movement?
Object-oriented database, unfortunately, did not pick up. There were a lot of attempts even before this NoSQL, but did not really succeed. So basically, I will be explaining this later on. What happened is there is something called, instead of having an object-oriented database, there are two things. Many other approaches that people do in practice, but not an object-oriented. There's no successful, widely used object-oriented database. So the way usually it works, you have an object-oriented, let's say, sorry, you have objects, yes? You have objects. If you have a running program developed using object-oriented paradigm, at the end of the day, you will be manipulating objects in your program, okay? And these objects have some state, let's say customer object. It has some state, some attributes that you want to persist into your database. So what we have, there are some well-known module or well-known libraries that come with, let's say, Java or .NET or Python. They call themselves object relational mapping. And what you do, you say, this is my object, it corresponds to this table in the database, and this is your database. So you come to not your object, of course you come to your classes. Remember, before you can create an object, you create a class first. You come to your class and you annotate, you do some kind of mapping. Let's say you have customer class, you have a customer table, and you map between the two. You say this is a class, or it's become, once you annotate, it is now called an entity. You have an entity and you have a table, and you link between them. And then this object relational mapping, where you just you use some API and say, I have this object, please go ahead and persist it. It will generate the SQL to do that. Okay, this is one way to do it. The other way, this is one way, very common way. I will give you some more details about it. The other way is you serialize the object into one of the common data format. And the most common ones are XML, out of fashion kind of format, and there is JSON. Yeah, and then so basically you have an object. It could be simple object or it could be complex object with an object hierarchy, like an order that I showed you. So you serialize it. Maybe many of you may be familiar with serialize. Any idea what serialize means?
You make it like a button format.
You transform it into transmittable or persistible format. You translate it into text, either XML or JSON, and then you persist it either in JSON in a document-oriented database or XML database. There was an attempt of XML databases, but also did not succeed too much because JSON came and kind of made XML sort of obsolete. Yeah. Just those of you not familiar with this, let me just give you a small example, just for those of you not familiar with this. So, for example, in object-oriented programming, if I want to represent a student, I will create a class, student, yes? And then basically I have attributes and methods in this class. So, for example, let's just keep it simple. ID, which could be, let's say, an int, and I have a string, first name, and I have another string, last name. Yeah. So now this is a class in my program, and in my database, I might have a table called also student. Okay, so this is one world and this is another world. This is the programming world and this is the database world. There's a gap between them. There's a big gap between them. How to bridge this gap? How do we get our objects? By the way, this class, when I want to use it, I create an object out of it. Something like those of you, something like, let's say, yeah, for example, Ali student, for example, or I put the class as the type, and then I create an instance of the class, typically, and then I start initializing it. Let's say the ID is 123, the first name, Ali, last name, whatever, okay? This is an object. In memory, this will occupy some place in memory with this attribute, yes? Now, this, at certain stage, I want to push this object to the database. Database is another world, another concept. We have tables. I will have a table in my database, let's say called student, and I will have columns, ID, first name, last name, okay? So this is one world, database. There are two different systems. Database is managed by another system, and this is my program that I'm writing. Okay, and there's a gap between the two. So how do I bridge this gap if I want to push this object to the database? Now, one way is to create statements myself. I create SQL statements myself. So I will translate this into an SQL statement. If it's a new student, I will say something like this: insert into the student table, and then you say values. This is SQL. And then I start putting the values. Okay, values here. Of course, this will be a string because SQL at the end of the day is a string. So I construct a string. Imagine it's a bit not very elegant. So I construct a string. Let's say this is an insert SQL. And the data type of this one is a string. So I construct a string myself. This is the first part of the SQL. I will do this some kind of concatenation. Up to here, this is SQL. And then I'll start concatenating the values I want to insert. So I'll do something plus, let's just keep it simple, Ali. Plus Ali dot ID or get ID. Anyway, it's a big story, but let's just keep it simple. Plus ID. Plus, I will do something like this. Comma, close the comma, and then plus Ali dot first name. First name. You see what I want to say here? You are writing an SQL statement in your code. You write an SQL statement, then you submit it to the database to insert it. This is so not very elegant way of doing it. Not very elegant way at all. Imagine you have, in reality, when you have a table, you have maybe 50 columns, 60 columns, maybe even 100 columns. You don't want to be wasting your time concatenating these fields and creating an insert statement. And same thing for update, same thing for delete. So you will be doing you as programmer, you will be doing the bridge between your object-oriented world and the database world and the tables. How do you do the bridging?
The relation mapping.
No, this is the traditional way. You write the SQL statements. You write the SQL statements by creating SQL statements, which are, what is an SQL statement at the end? It's a text, it's a string. So you create the string yourself. Yeah. Is this clear, or should continue for it to be clear?
This in the project, right?
No, we will not. This is like a kind of a traditional way, okay? A better way is to use some framework, object relational mapping, okay? And what you do here, you come to this, like one of these example frameworks. Let's say if you use Java, it's called GPA, Java Persistence API. So what you come to this class, and say at entity. Once you put this annotation, you are telling this GPA, by the way, there is a corresponding corresponding table in my database with the same name as the class. So I have student class and I have a student table, okay? And then all you do, like for example, in this GPA, there is one of the major classes that GPA provides called entity manager. Something like this. All you do, you say entity manager dot persist. Persist. And you give it the name of your object. Let's say Ali. That's it. What this entity manager will do?
Create the table and insert the...
Yeah, we'll basically create the insert statement for you. Yeah. If it is an existing object, you can change the values and you just say entity manager persist. And then this entity manager, what it will do? Generate the update. You got the idea. Yeah. I will give you more details later, but I just want, maybe it's a long answer. So the object-oriented database, there is no such thing. It did not fly. Okay. So this object relational mapping, because the relational model is so strong, it has very strong mathematical foundation, as we will see later on. And this mathematical foundation allow you to optimize the queries in a very elegant way. So, and the relational model builds immediately on top of those mathematical foundations. So it is very hard to compete with. Very hard to compete with in terms of data model, in terms of query language, and in terms of query engine. Okay, so the only movement that really managed to break the monopoly of relational model is some of NoSQL database and some of the NewSQL database, not because of the data model or because of the query capabilities or any of those. What was the main reason? Is the scalability. Okay, it's not as scalable out of the box as alternative ones. Okay, so just to complete this picture, you got the idea of this object relational model, relational mapping. It will liberate you from writing this very fragile and very rudimentary way of kind of creating your own SQL statements by yourself. The other way to do it is you serialize. You serialize means you see this object here I have. This is an object, Ali, and this an object will be something in memory. So in the computer memory, some memory location will be allocated to this object, and I will have something like this. So in memory, imagine this is your memory, the computer memory, and then basically I will have an object called Ali, and this object has attributes: ID, 1, 2, 3, first name, Ali, and last name. Now this exists in memory. Now for me to store it in disk or to transmit it through the network to another node, or I have to do one important step called serialization. I have to write it in a way that is transmittable, because this is a memory location. I cannot just take it and kind of send it. So I have to serialize it. And serializing it means, in modern serialization, is basically translated to a text, to a string. So there are two major ways of doing it. Either you serialize it to XML or you serialize it to JSON. Okay, XML. If you use XML, your message or your serialization will look something like this. You will have something like student, and you open a tag and you close it. This is a student, and then this is the object, and then inside you put ID, 1, 2, 3, and you close the tag, and then first name, Ali, and then you close the tag, and then last name, Faleh, and you close the tag. Yeah, this is XML serialization. You close this tag. This is XML serialization. There is something called binary serialization. Java can serialize it to a binary object, but you have to have Java on the other side. The recipient needs to have the same technology to be able to deserialize it, to be able to reproduce the object. You get what I mean? So if you have objects in memory and you want to transmit it to another node, if you use what is known as binary serialization, you have to have same technology on both sides, because the data types are different. Every data type has a different size in memory, and that size is language dependent. So you have to have, and the way the binary serialization work is technology dependent. Java does it in one way, C# does it another way. If you use, like, let's say, binary serialization, you won't get that easy interoperability between programs written in different languages. And text is the most universal kind of format. You send this message to any program, it will make sense of it. It will know that it needs to construct a student object, and these are the attributes, and these are the name of the attributes, and this is the name of the values. Okay, so there are XML databases where you can take this is a document. You can take it and store it and retrieve it and query it and so on. Okay, now this is XML, but you can see it's very verbose. There are more tags than the actual content. Okay, so then JSON came along, which is a much more lightweight. So an object, you just open the curly brace, and then you start saying something like this: ID, colon, 1, 2, 3, and semicolon, and then you put here first name, colon, Ali, and last name, colon, Vale. And that's it. This is what you transmit. Or this is what you store in your database. This is JSON format, much more lightweight than. So that's the reason why in relational, the object-oriented databases, there were attempts, but not very successful because there are better alternatives. Either you use an object-relational mapping to bridge the gap, or you serialize and store it as it is in one of the databases. In fact, the document-oriented database, most of them, they use JSON format. You store it as JSON format. In a MongoDB, which is a document-oriented database, what I have here, this is a collection of books, for example. So my database is made up of collections, and inside each collection I have documents. Okay, here is the book. Here are the books, and you can see here the documents are stored in JSON format. So you can see here. Here's my book, and I have here a book has a unique identifier. This is auto-generated by the database. And then I have my authors. You can see here it can be multi-values. In a relational database, this is not allowed at all. In a relational database, every column is atomic. You should not have multi-values. You cannot have arrays or multi-values in a column. In here, you can see here store. In here, this is a kind of referring to another collection. I have another collection called store. Yeah, I can do the join. In the past, in MongoDB, you cannot do join. You have to do the join yourself in the client side. But in the latest version, you can do server-side join. So you can see, like, the relational database, joining tables and doing complex queries by joining multiple tables is a very fundamental feature and a basic skill any SQL developer will learn from day one. But in a document-oriented, that feature was not there. Only recently they implemented it. So you cannot join documents, but lately you can do so. So I just want to show you, like in here, you see here, publisher is an object. So I have a book. Inside one document, it has everything. It has the list of publishers, the list of authors, the store in which I can find it. Yeah, in one document, I put all this together. So to summarize, in a document-oriented, I keep the aggregates. Aggregate means in those of you who has some experience with object-relational or object-oriented programming, some objects are called aggregates because they are made up of other objects. So, for example, an example, order. Order is an aggregate entity. There is whole and parts. The whole is the invoice, is the order, and the parts are order details, order items, and order items is one-to-many, multiple items, and there is payment. So in a document-oriented, you keep the aggregate together, and you persist it as it is in one go, and you can retrieve it as it is. But you can, as I explained also, you can query inside the document, no problem. You can query inside the document. And with the new capabilities of modern document-oriented database, you can also join. Yeah? So that is the power of document-oriented, and it's really picking up because it has built-in partitioning and built-in replication built-in. Okay, and plus in terms of programming, it's much easier compared to this. As I explained, to insert this, you need 12 inserts, and to bring them back, the query is quite complex. You do lots of joins and so on. But if you keep it as it is, it's simple. Simple to insert, simple to retrieve, and more efficient and more scale. You can do it scale. You can make it scalable. Yeah. All right. So that is the idea: keeping the aggregate together. Yes, please.
That means aggregate now For example, it's like many objects inside.
Yes, many objects that are related, of course.
Yeah, related,
yes, yes, and they belong to one entity. Yes. Another good example is the CV. You know CV? So it has many parts. Let's say education, experience, projects you worked on, and so on. Yeah. If you want to do it in relational database, the schema can be quite complex. Okay, you have, let's say, person, and then the education part will be in one table, and then the project in another table, the experience in a third table, references, and so on. Yeah. So you have so many tables, and if you want to add the CV, good luck. You have to add too many tables. You insert into many tables. But if you want, you can keep the whole CV in one document. It has the details of the person, all the education they went through, the experiences, the projects, the references, the languages they master, the hobbies, and you name it. Okay. And a good thing is, if some of those sections are not relevant for a particular person, you just don't mention them. Yeah. So CV is a good example because our CV is not identical. For example, programming languages. For profiles like us, like working in computer science or information technology, we will have a section programming languages. But for managers, that section does not make sense. Yeah, and so on. So in here, there is no enforced schema. In fact, if you look here, if you look in there is no schema here. It's up to you. Database does not care. Of course, developers are aware that there is a schema. But in a database, in a relational database, there is a schema, as I showed you before. It's just a small example here, movie example. Or database, you can come to it and say, give me the schema of this database. What are the tables? What are the relationships between them? And it can give you, visually even. The graph-oriented database. In the graph-oriented database, something like this, like what you see here, you can basically have it in your database. You have nodes, and those nodes have relationships between them, and you can have attributes related to nodes, or you can add attributes to nodes or edges. Okay. So in here, you're talking about instances. Say, for example, Iradi works as QU. And you can put here the date he joins, okay? And you can have attributes of this particular object, this particular node, and you can connect them basically. Okay? And then you can deploy this to your database, and there is a language where you can query this. But the queries here are very, very different because this is a special case. This is a narrow niche application area. If your data is really connected and it looks like a graph, let's say, for example, transport network, where you have transport network is made up of routes, and those routes have stops, and there are segments between the stops. So when you look at it, even in a map, even in some kind of the public transport map, it looks like a graph. So rather than trying to if you want to store it and manage it and query it, instead of trying to kind of squeeze it into the relational model, you keep it as a graph, and you store it as a graph, and you query it as a graph. But the queries are very different. You can say, give me the closest location to QU, or give me the shortest path from QU to Village, and the database can give you that stuff. So this is a special case of databases, and it's not applicable to all scenarios. Very special scenarios when you have really connected some kind of graph that you want to persist and manage and query. And even the query language is very different. So you can see here the most, really the one that's really challenging in a very successful way, the relational model, is a document-oriented database. The others are also very relevant, but they have their own special cases, not as general as versatile and as flexible to use it in many contexts. Okay. Moving on. Okay, just to summarize. So important design goals that these NoSQL databases had in mind from day one: scale out. You can scale it out to commodity hardware. You don't need to get this fancy HP or Dell, the latest servers. You can just have normal servers, many of them, and you put them together and deploy your database. Low latency updates and sustain high update insert throughput. Because your database will be replicated, especially for reads. You can read from multiple nodes, so you can handle more requests. Even for writes, but for write depend on the configuration. Let's delay it, otherwise we will keep going here. Let's delay this to another discussion. For writes, you can write to all nodes, but that will give you a problem of consistency. Okay, the nodes will of course exchange the updates and come to a synchronized state, but it will be eventually consistent later in the future. But at some point in time, you might query different nodes and get slightly different results. In some application, it could be okay, like let's say something like Facebook or Twitter. It's not the end of the world if I query the server in Qatar and I don't see the latest tweet from some person. It's fine. If those tweets are available in another server, it is okay if we don't get exactly the same view. But in financial and order processing systems, for example, it is very critical to always have consistent state. There is no room to have something eventually later in the future they will be consistent. Okay? Or you can have what is known as a master-slave architecture, where you write to one server, and that server will propagate to other servers. And again, it's up to you. You want to wait for all of them to confirm that they got the update, or you just, if the master got it, you trust that the master will push it to the other servers. So the consistency becomes like configurable. It's up to you what your application tolerates. Okay? There is a trade-off, as I explained shortly. Also, you have higher availability because you have replication. Because your data is replicated, if one node dies, your system is still available. Maybe the throughput and the performance could degrade a bit, but it's still available. Okay? It doesn't mean in relational database you cannot have this. You can have this, but more costly and not out of the box. Yeah? And even when in a relational database, of course, in a real world, you will find replicated database, but they are not used at the same time. One of them is active, the other one is on standby. And the active one keeps pushing the updates to the standby one. If one server dies, the other one picks up. There is this, of course, that in the enterprise, there is no serious company out there that's not doing replication. Yeah? But it's not the type of replication I'm talking here. Yeah, it's different. In here, you can have multiple copies of the same data, and it's auto-managed. And it's live, like you can query those multiple copies at the same time. You can get some of your users, when you have a query request, you can route it to different nodes and get the results. Yeah? Okay. Now, nothing comes for free. Okay, with these NoSQL databases, many of them are ready to sacrifice some of the asset properties. Remember the asset properties that were at the heart of the relational database. In here, some of them kept it, some of them made it configurable. It's up to you how you want to configure it. Some of them, they just dumped it. They said, we don't want it. We want to trade it for better scalability and higher availability. In fact, there was a famous paper, you can look this up, where mathematically, this is proven. When you have once you have a partitioned system, once you have a partitioned database, what do I mean by partitioned database? Distributed in multiple nodes. Yeah. Once you have this, and you have, of course, a network between them. So once you have a partition, you can only achieve either consistency or availability. You cannot achieve both at the same time. Okay? And this is called the CAP theorem. There's a paper, famous paper, discussing this. Let me give you a concrete scenario to really understand this concept. So once you partition, you can only have one of the two, either consistency or availability. First of all, what do we mean by consistency? In this context, when you have multiple nodes and multiple copies, what does it mean?
The change will be for all.
Change will be for all, or another way to say it,
All copies are same.
Will read the same value.
we read the same value regardless of which node which copy you go to. That's what consistency means in this case. What about availability? Works all the time. Your system is up and running regardless. Even if some nodes are down, your system is still up. Okay? If your data is partitioned and replicated across multiple servers, you cannot achieve both at the same time. You can either take one or the other. Okay, let me show you an example.
Excuse me, Doctor, the consistency here, what does it mean?
Okay, consistency means once you have a partition database and replicated, so you have, for example, the customer details. You have something like, let's say, customer table, as an example. It has the details of your customers. And this customer details is replicated, which means multiple copies in 4 servers. Now, when people come and query yours, give me the customers that with the name start with A. You can come to any server, it will give you the answer. Yes? Consistency means here, if you ask any of these 4 servers, they should give you the exact answer. No difference between them. Yes? That's what consistency means in this context. Yeah? Now, when you have this architecture where you have your distributed database in multiple nodes and network between them, you can only achieve one of the either consistency or availability. So let's take a scenario. So we have 2 people. Let's say we have in a booking application, in a hotel booking application, and hotel, there are rooms you can book. Now this hotel room data is replicated on 2 servers. Yes, and now the scenario is we are. This is the last room available in that hotel, as an example. Yeah. And we have 2 people looking at 2 servers, from 2 servers are interacting with our system. And both of them at this stage, they are seeing that the room is available. Yes? And then, so let's say I queried hotel XYZ, and it says between this date and this date, and it says the room you want is available. And the same query, somebody from some other location, let's say one from Doha, one in US, for example, okay? And you have 2 copies. And they are looking at 2 copies. And then suddenly, these nodes, the one in Doha and the one in US, the network between them is down. They cannot interact with each other anymore. Yeah? And now I see here, let's say there is Ali in Doha and there is John in US. Yes? And then they are seeing that the room is available. And now it's time to book. Now, there are two solutions to this. Because the network is down, what are the 2 solutions? What you can, as an application developer or as an application, what could be the behavior? How can you handle this scenario?
To only take one node.
Sorry?
To only make the condition with one node.
Make.
Yeah, you make the whole process with one node.
make the whole process with one node? No, we have two nodes. So what happens is, if I let both of them book the room, what will happen?
They will book the same non-conflicting.
Sorry? I will have in this scenario, I will have an inconsistent states, undesirable states where the last room is booked twice, which will basically, I will have an overbooking. Okay? So if I let if I let both of them, if I let this, let's say Ali in Doha book the room, and John in US book the room, and remember this is the last room. What I will be, what I will end up with as a hotel,
Inconsistent.
I will have inconsistent state in the sense that this particular room is booked twice. Yeah? If the network was up, I could have checked. Once I book here, I can synchronize. Let's say John quickly booked, then I let the other server know. It happened many times, and maybe it happens to me many times. You try to do something, let's say you try to book some tickets, and then you say submit. Once you submit, it comes back to you and say, sorry, the price has changed, or the seat is no longer available, because somebody else maybe took it.
I say the server that another server.
Yes. If the network is okay, then you will not end up with this situation. But if the network is down, if you favor availability, what's in this case availability means you don't tell the users, oh, sorry, you cannot book because our nodes are not communicating anymore. So if I let them both of them book, what I am favoring?
Inconsistency.
No, I'm favoring availability and paying the price of consistency. The other solution is I tell them no, don't book, please come back later. So in this case, what I'm favoring? Consistency. What I'm sacrificing? Availability. So in this theorem, which has been verified, once you have partitioned data and replicated data, you have conflict between these two goals, consistency and availability. You cannot achieve both when there is network failure, either one or the other. Okay. In most cases, what do you think? This is the business decision, not a technical decision. The business people will make the decision. Whether you want, when there is a network failure connecting those nodes, when there is a failure, if you favor availability, which means you let users do whatever they wish to do, then you might pay the price of consistency. Because once the system come back alive, they will realize, oh, I have a problem here. This room is booked twice when they try to synchronize between them. Okay? But this is a business decision. The business might say, okay, no problem. It's not the end of the world. We will send maximum we'll send an apology email saying, here is $10 discount. Next time you book with us, I'm sorry for this. Or they might even say, no problem, leave it as double booked. Hopefully somebody will cancel. Or maybe we can take that customer to another partner hotel or take them to somewhere else. Yeah. So there are other ways of dealing with inconsistencies. But it's up to you. Usually it is a business decision whether to favor consistency or to favor availability, but you need to be aware of this. Once you partition your data, you are faced with this dilemma of these two conflicting goals, and you can only achieve one of them, not both at the same time. Is this scenario clear? This is what this theorem is really. So in here, the consistency becomes tunable. It's not like that. In relational, it says, halas, consistent all the time. It's not negotiable. In here, it's tunable. It's up to the application. If your application tolerates some inconsistencies or tolerates delayed consistency, it's fine. If your application does not tolerate, then you'll need to sacrifice availability when there is network failure between the nodes. Yeah. Okay, moving on. Now, this is in around 2010, and it's a big movement. And of course, this movement created a new ecosystem, a new set of alternative databases that we can consider. And then there was the counter movement, which trying to say, no, we really need to keep the asset properties. We want to keep the relational model. We want to keep SQL as the prime language to interact, to query the database. And then basically we'll re-architect the whole database engines and address the problems to make them scalable. Okay, and this produced a new vague of databases, such as this VoltDB, Google Spammer, MemSQL, NeoDB, and so many of them. Okay, it is still an ongoing battle, but it's picking up, and this is really where the future is. Yeah, you can achieve your desired scalability, and at the same time keep this strong asset properties and relational model and so on. So at the end of the day, you can see here databases differ in terms of data model, querying capabilities and languages, and approaches to scale. They have different ways of doing it. We have the relational model, 50 years of existence, very mature, like very robust. There are plenty of mature commercial and open source products. If your database fits on one server, that server can handle the load you have. Relational model is really, really excellent. Now, it gives you this acidity, of course, with some cost. This acidity, acid properties come with some extra performance cost, and also not easy to scale outside one server. Then we have this new movement of distributed databases manifested in two. First movement is NoSQL, and then the counter movement SQL. So the NoSQL, the distributed database in general, whether it's NoSQL or NewSQL, they have this scale out using automated partitioning and replication built in. That's the major difference. And you can easily distribute them across a cluster of machines. And for the application, it looks one. The application is not aware that there is a cluster. That's the advantage of this. Now, the NoSQL focused on low latency and trade-in consistency for scalability. It's ready to even throw away ACID properties for the sake of scalability. And it came up with different data models and different query languages. They said, okay, SQL is not necessary, it's not the only way to do it, and relational is not the only way. There are other models. And the NewSQL, as I explained, is nothing but a relational database, a relational model, SQL, ACID properties, but the whole engine is totally re-architected for modern hardware. Because remember, the original relational database were invented in the 70s and picked up in around the 80s. Took many years for them to have a wide adoption. So they were architected with the hardware design at that time. But the hardware also has evolved. The memory, CPU, multi-core. So these new databases, they try to take advantage of this re-architected modern hardware. At the same time, these bottlenecks of relational model, especially the lock-in-based mechanisms and log-based recovery, has been removed altogether, thrown away, and some more better mechanisms put in place to allow scalability and to allow availability. And hopefully this will be covered more in the review papers that you will be doing. And here we back to ACID properties, we back to relational model and to SQL. So that's basically the whole movement, kind of briefly the history of evolution of database. And the key conclusion here, there is no one database. The dominance, the result of all of this, the dominance of the relational database is gone. Khalas. Like, it depends on the application you want to do. Different data models, different architectures, different products based. You choose the one that is relevant for the application you're at hand. Yeah? In fact, there is something also called, there is even a book about it. It's called polyglot persistent. Polyglot means multi-database per application. Similar, those of you who are really into programming, in a real implementation, you will not be using one language, especially in the web. You'll be maybe using JavaScript, Java, and maybe C# and multiple languages to build an application. Same, one application, multiple languages. Same thing is now happening to databases. One application, multiple databases. Okay? So for example, your orders could be managed in a relational database. The user profile could be managed in a key value store. I gave you the example last time of Amazon. Once you go there, you have the session ID, and then they look up your profile. Your profile, you have your preferences, you have the, let's say, the items you visited before, maybe it's have items that you put in your cart. All of this can be pulled from a key value store. Yeah? So you don't need to just put everything in a relational database. You don't need to. You choose the most relevant one. You choose the relevant database for part of your application. So you will end up maybe with multiple database technologies used in the same application. That's basically the key result of these two movements, the NoSQL movement and the SQL movement. And you might end up with multiple data models, not just relational model. So you need to be aware of all of them.